Swayam Prabha. Digital India. Educated India.
Okay. So, now let me actually write out a convex optimization problem. So, consider this convex optimization problem, minimize fx subject to gi of x less than equal to 0 and ax equals b. So, I going from 1 to m, ax equals b. So, A now is a matrix in R p cross n. So, it has p rows and we will assume that A is full row rank. Okay. So, in short, rank of A is equal to p. Now, we will assume, so suppose f and all these gi's are convex, okay, and suppose p star is greater than minus infinity and attained. Okay. So, that means the optimal value of the primal is finite and it is attained by some point x that is feasible. Now, first little observation that is quite easy to make is that, and I will leave that as a claim, it is very easy to prove, that if f comma gi is I going from 1 to m, if these are convex, then G, the set G is convex. Okay. So, to if you want to see this is not hard to show, but if these, so how does one show this? If you, maybe we can quickly take a look here. So, what we need to argue is that if u1 v1 t1 and u2 v2 t2 are in G, then any convex combination of thereof is also in G. So, maybe I will just show you the proof of this. Let us quickly do a proof of this. So, let suppose u1 v1 t1 and u2 v2 t2, suppose they both belong, so they all belong to G. Then, okay, and let alpha in 0 comma 1 and define, say, u bar v bar t bar as alpha u1 v1 t1 plus 1 minus alpha u1 u2 sorry u2 v2 t2. Okay. We need to show that u bar v bar, so we need to show that u bar v bar t bar belongs to G. Okay. So, How would you show that? Well, you look at u bar. So, what does it mean to show this? We need to show that there exists, that is, we need to show there exists an x such that fx is less than equal to t bar, gi of x less than equal to ui bar, and a x minus b, okay, is equal to a x minus b is equal to v bar, right. So, what have I done here? See, notice that this was my optimization problem in the original form. So, to bring it in the form as before, I have basically written this as a x minus b equal to 0. Okay. So, I had my when I took points u1 v1 v1 t1 and u2 v2 t2, the 0 got replaced by v1 and v2 respectively, and now for this particular point I am looking for v bar. Okay. So, since u1 v1 t1 and u2 v2 t2 lie in G, so clearly we have that there exists x1 and we use a superscript x1 and x2 such that f of x1 is less than equal to t1, gi of x1 is less than equal to ui1, and a x1 minus b equals v1, and similarly f x2 is less than equal to t2, gi of x2 is less than equal to ui2, and a x2 minus b is equal to v2. Okay. So, now remember t bar is what? T bar is alpha t1 plus 1 minus alpha t2. Similarly, u bar is alpha u1 plus 1 minus alpha u2, v bar is alpha v1 plus 1 minus alpha v2. So, what I will do is I need to show that there exists, okay, let us call this x bar, there exists an x bar such that all this, right. So, what I will do is take x bar as alpha take x bar as alpha x1 plus 1 minus alpha x2. In that case, what would I get? Well, f of x bar, since f is convex, I would get that f of x bar is less than equal to alpha f of x1 plus 1 minus alpha f of x2, and that itself is less than equal to alpha t1 plus 1 minus alpha t2, and that is what? That is simply t bar. Okay. Similarly, gi of x bar is going to be less than equal to alpha gi of x1 plus 1 minus alpha gi of x2, and that is equal to, and sorry, that is less than equal to alpha ui1 plus 1 minus alpha ui2, which is nothing but alpha u bar, sorry, which is nothing but, it is not alpha, which is nothing but u bar, right, and a x bar minus b is actually equal to a alpha x 1 plus 1 minus alpha x 2 minus b, and that is equal to, now what I will do is I will write this, I will split this b as alpha b plus 1 minus alpha b, and that would give me a alpha times a x 1 minus b plus 1 minus alpha times a x 2 minus b, and this is equal to, as you can check, a x 1 minus b was equal to v 1, a x 2 minus b is equal to v 2. So, it will be alpha v 1 plus 1 minus alpha v 2, and that is nothing but v bar. Okay. So, in other words, so we can we needed to show that this particular thing is true, and we that means that required us to show that there exists such an x bar that satisfies all of these, and we were able to show that by taking x bar to be alpha x 1 plus 1 minus alpha x 2, where x 1 and x 2 are actually the points that the x 1 and x 2 that give you that, because of which u1 v1 t1 and u2 v2 t2 are in G. Okay. So, what has this done? This has given us that by doing this, what have we shown? We have shown basically this claim here. Okay. So, just to make sure everyone is on track, this is the claim that we have shown, that if f and these g's are convex, then if these f's and gi's are convex, then this set G is also convex. Okay. So, now let me move forward to the duality problem. Okay. Now, let me define this another set. Okay. Let me define this set T as capital T as follows. It is 0, 0, S such that S is less than P star. Okay. So, what is this? Well, this is nothing but an open segment along the T axis. It is a 0, 0 S such that S is less than P star. So, it is a segment that goes from minus infinity. So, if you, or rather let me go back to the figure that I had drawn here. Well, it is a segment that starts from minus infinity and goes all the way up till P star, but does not quite touch P star. So, it is open at P star. So, it is this segment. Okay. Now, this segment is obviously a, so this is obviously a convex set, all right. Now, but now the main, the thing that that's important for us is that T intersection G, okay, the claim is that T intersection G is empty. Now, this may seem very natural because of the kind of figure I have drawn here. Okay, no wonder it has to be, you would think that yes, T intersection J is non-empty, but it needs a bit of proof. See, for example, that G could very well do this, right? It could go down here and then intersect here again and so on. So we have to be a little careful and rigorous about this particular argument. So, let us do that. Okay, so T intersection G is empty. So, suppose proof again. Suppose U V T belongs to G. Okay. belongs to suppose u v t belongs to t, then it means that or rather let us put it this way, let us start with suppose u v t belongs to t intersection g. Okay. Now, if it belongs to t, then it means that u equals 0, v equals 0, u equals 0, v equals 0 and t is less than p star. Okay. But since it also belongs to G, it implies that there exists an x such that f(x) is less than equal to t. So, there exists an x such that f(x) is less than equal to t, gi of x is less than equal to 0 and ax minus b is equal to 0. Okay. But then t itself, okay, is less than p star from here. So, if t is less than p star, it means that there exists an x which is feasible. So, by this feasible for p such that the value of such that f of x is less than the optimal value of p. So, what does this mean? It basically means that if t intersection g is not empty, then you should be able to find an x whose optimal value is actually less than the stated value p star. Okay, and that is absurd because p star is the least possible value. So consequently, this is not possible. So, this is a contradiction. Okay. All right. Okay. So, now, so what does this mean then? This means that t intersection g is empty. Now, t itself, because it's the kind of segment that I mentioned from minus infinity, it's an open segment from minus infinity to p star. So the set T is a convex set. We just said that we actually just showed that G itself is also a convex set. Okay, so T is a convex set, G is also a convex set. So T is a convex set, G we showed is a convex set, right. So now what we have are these two convex sets whose intersection by our claim here is empty. So there are these, so we've got these two convex sets that don't intersect, which means what? Which means, so then what does that mean? That means that we are in the regime of now the separating hyperplane theorem. What is this saying? So which means that there exists a separating hyperplane. Okay. So what does this mean? So there exists a separating hyperplane or a hyperplane separating for T and G. So there is a hyperplane that separates T and G. So that means there exists, let us call this, I am going to use this notation lambda tilde theta tilde say let us call this and let us call this mu tilde, say, such that so there exists this lambda tilde theta tilde mu tilde such that this hyperplane, remember from the separating hyperplane theorem, says that this hyperplane should have a non-zero slope. So, that means such that this is not equal to 0, okay. And so there is a hyperplane with a non-zero slope such that now if I look at the set G and look at the set T, they lie on either side of the hyperplane, right. So, if I look at the least value of this hyperplane over the set G, so you look at infimum over u v t in G of lambda tilde theta tilde mu tilde transpose u v t, this has to be greater than equal to the largest value over u v t of the same function lambda tilde theta tilde mu tilde transpose u v t as u v t ranges now over T, capital T. Okay. So, this is the separating hyperplane theorem. So, what is this effectively saying? That the entire set G lies on one side of it and the entire set T lies on the other side of it, and there is a weak inequality here because they could both the infimum and the supremum can end up being equal, alright. Okay. So, now let us evaluate these things carefully. So, u v t belongs to capital T if means what? That it has to be that u and v are 0. So, this particular quantity on the right hand side is actually just supremum over t less than p star. Okay. So, u v t belongs to capital T means that u is equal to 0, v is equal to 0 and t is less than p star, right. So, it is this t less than p star of mu tilde into t. Okay. Now, I haven't yet, we are not yet in a position to evaluate this. So, but let us leave it at this particular stage. Okay. So, now let us look at the one on the left then. What is the what's the one on the left? So, why are okay just okay yeah why aren't we in a position to evaluate this? Let's understand this for a moment. So, why aren't we in a position to evaluate mu tilde into t, the supremum of mu tilde into t over for t less than p star? The reason is because we do not know the sign of mu tilde. See, if the sign of mu tilde is if mu tilde was were positive, okay. If mu tilde were positive, you would evaluate this quantity, you would maximize it by putting t equal to the supremum would be at t equal to p star, all right. If mu tilde is negative, all right, if mu tilde is negative, then the problem becomes very different. So, let us just hold our horses here before we analyze, before we go ahead and analyze this. So, let us first look at what is on the left. Okay, what is there on the left? Well, this whole thing I can spread out and write this a little bit. Let's write this out in a little more explicit form. So, let us write this as lambda tilde transpose u plus theta tilde transpose v plus mu tilde times t as u v t belongs to G. Okay, and so I should put this as a greater than equal to. Okay. Now, if you look at let us observe this particular equation here. So, on this quantity here, this u v t belongs to G, right, which means that u can be so. Go back to the definition. If you go back to the definition, see what did we say is how does G look? G is unbounded in the u direction. So, whenever there is a u in G, a larger u can also be fit in because of the way the set has been defined, right. These inequalities will continue to hold. Similarly, if you have a T in G, then you can always fit in a larger T. So what this means is G is always unbounded in the u and T, along the u and T directions going towards plus infinity, right. So, what this means is that if u v t belongs to G, if u v t belongs to G here, then u and T can be made arbitrarily large. Okay. So, their values can be made arbitrarily large. So, now if their values can be made arbitrarily large, what does this mean? If their values can be made arbitrarily large, what's the only conclusion that can be drawn from here? Well, the only conclusion that we can have is, so so let us think of it this way. So, if either lambda or mu were negative, lambda tilde or mu tilde were negative, okay. So, if lambda tilde or mu tilde were negative, and the fact that you can drive u and T all the way to plus infinity would mean that the infimum here would actually be minus infinity, right. So, if lambda tilde and mu tilde were negative, then the infimum here would be minus infinity, but then the infimum is lower bounded by some particular finite value here, remember. So, the infimum is lower bounded by some particular finite value, which is the supremum of this linear function over T, right. So, since this is a supremum, the supremum cannot be minus infinity, right, because you can always take any real value and evaluate it to something finite. So, the fact that this is lower bounded by some finite value means that you cannot possibly have lambda tilde and mu tilde as negative, either of lambda tilde and mu tilde as negative. So, if lambda tilde less than 0 or mu tilde less than 0, then LHS equals minus infinity, which is absurd since RHS is finite. Since RHS is finite, right. So, if this can be minus infinity, so this cannot be minus infinity, right. So, which means that both lambda tilde and mu tilde are greater than equal to 0. I write this separately, lambda tilde greater than equal to 0 and mu tilde also greater than equal to 0. Okay. So, now if mu tilde is greater than equal to 0, then that tells us also something about what we were talking about here. Well, if mu tilde is greater than equal to 0, then the supremum here is to be equal to mu tilde times P star. Okay. So, that has simplified our expression a bit. Let me change my color, and so you can keep track. Infimum of, so the left hand side has now become lambda tilde transpose u plus theta tilde transpose v plus mu tilde times T greater than equal to mu tilde into P star, and the infimum here is over u, v and T belonging to G.